What we're talking about is trying to use machine learning techniques to get quantum computers to do the job they're intended to do better. Before we get into the actual work, I want to kind of highlight the people. So the head of the institution at Jülich is Frank Wilhelm, and these are the students that took part of the work and the funding. All right, so everything I'm going to tell you about is open source, and you can go to qoptimize.org and download it if you think it's useful for you. All right, so the kind of basic terminology, so we're sure we're using the same terms for everything. We define optimal control as something that's model-based, and then you do some open loop simulation, and you try to achieve the best possible controls to perform some operation. Let's say you want to do an entangling gate or something like that. You have calibration, which is a closed loop optimization where you use the actual quantum device to iteratively improve the controls. And it has the advantage and disadvantage of being model free. This is advantageous if your model is really bad, which is often is. And then we have characterization, which is the process of determining the accurate model for the quantum device. In this field, we currently have the problem that, for example, when you manufacture superconducting qubits, they come out kind of like snowflakes. Each one is slightly different. Different enough that they require slightly different control pulses. So characterization plays a major role because we need different controls for each qubit. And actually, the parameters also drift as a function of time. So we need to kind of fine tune the controls every day. Otherwise, the fidelity of the gates goes south pretty quickly. Now, as you can see in the terminology, the concept of a model is really important, but we need kind of to properly define what a good model is, because we want to have the possibility of actually declaring success where we found a good model. So a good model is one which predicts the behavior of the system. That's quite obvious. For the operations we want to perform, that means that there are certain energy limits and bandwidth limits and various other kind of constraints on what we want to do with the device and to the accuracies we care about, right? So every model is an effective simplified model. We're not doing quantum chromodynamics for every atom on the superconducting chip, right? So it's a question of accuracies. Here we usually mean something like 10⁻⁴ in terms of fidelity. That's the accuracies we're looking for. And the operations are obviously gates and reset and readout. Okay, so what is the motivation for this work? So currently, and I'm talking kind of 2020, the limiting factor in performance of quantum computers is the gate fidelity. And I want to prove this claim. So IBM's best quantum volume is 64. Let's not kind of go into detail exactly how it's computed, but what it means is that if you do only 36 entangling gates, your fidelity drops below 2/3. Okay, and that's not really impressive, right? 36 gates is not a lot. Now, if you take the Google quantum supremacy experiment, they achieved this result when they took 30 million shots, of which 99.8% were noise, but they have enough statistics so they can prove that the 0.2% were actually fully quantum. Okay. So, I mean, the Google result is really impressive, but when you kind of go down a little bit into the details, you see that there's still a lot to be desired. And these results are actually kind of the best of the field, right? So it's not putting down IBM or Google in any way. It's just kind of a picture of where the field is. Another way of looking at it is John Martinez, who headed the Google group, had a paper in 2014, something like superconducting qubits at the threshold of error correction. And there, the entangling fidelity was 994. in the supremacy experiment, kind of the median entangling fidelity was 994. Okay, so we're 5 years apart, and the fidelity hasn't improved. Now, to be fair, in the first paper, it's just one gate operating alone. In the second one, it's 53 gates operating in parallel. So there's crosstalk and there's kind of more complex issues. But still, we haven't improved like an order of magnitude, which is something we really would like. It would make error correction a lot more simple. Okay. Now, why is this? Why are we stuck? Because the way we currently calibrate the devices is not very good. This is a graph from the Google supremacy paper, and each little circle here is a manually coded custom calibration script. And you might be able to see this is a directed graph, and they need to repeat some operations, etc. And the kind of each of these circles kind of takes like a PhD thesis. Okay, so we're talking kind of a lot of man years. Now, this is super specific. It requires huge resources to set up, meaning if you're not Google sized or IBM sized, you're not really going to be able to do that. And kind of in my perspective, the worst of all is that we don't really learn much about the chip from this. We just know how to make it work. And characterization, which is kind of doing something similar in order to learn what's going on, that's similarly hard. And as a result, it's almost never done. So people publish papers, virtually everybody, publish papers about chips for which they don't have a good model. I'm actually not aware of a single good model as defined previously that was ever published. And if we don't understand what's going on, we can't understand what's going wrong. We can't understand the sources of the limits for the fidelity, which means we can't fix it. Okay. So I'm part of the Open SuperQ project, which is a kind of EU quantum flagship project trying to get a superconducting quantum computer with about 50 qubits. And we don't have the manpower that Google does. So we need to think of something that's a lot more automated and kind of more sophisticated. And there we're kind of looking into borrowing a lot from machine learning techniques to get the job done. So the main tool that we constructed is called C3, which stands for Control, Calibration, and Characterization. And there are 3 steps. First step is you take a model, you do what we call C1, which is an open loop model-based optimal control, and you figure out how the control pulses for your hardware look like. For superconducting qubits, it can be the shape of microwaves. For trapped ions, it's usually lasers, etc., etc. It doesn't. The specifics aren't very important. And what you end up with is a set of pulses that implement a gate set. Now, because our models are not very good, then the step 2 is to take this gate set and to try and improve it further with a model-free optimization that is done directly with the quantum device. So we're not limited and hamstrung by what the model can give us. And everything we see during the calibration, we store in a data set. And the third stage is we take this data set and we do a stage which we call C3, which is model learning, right? Another way of calling characterization, meaning we're trying to modify and fit the model so that it reconstructs what we've seen during the calibration, the second stage. Now, if you have what we call a good model, then the open loop will create a gate set that actually works as well as can be on this hardware. Calibration will do nothing, right? So we kind of repeat this process until it converges in the sense that there's nothing can be improved with calibration. Okay. Now this is kind of a little bit nebulous, so I'll go through a specific example, and we'll look at the synthetic device, and we want to use a synthetic device kind of simulated so that we know what the true model is. And it'll be kind of a little bit sophisticated. So you'll have, can you see my mouse? I hope so. So you have two qubits and they're coupled. We have the coupling G here. Now, every time you measure, you only get 1 bit per qubit. So you need to repeat the measurement a few hundred times. You get shot noise. So that has to be included in the model. You need to include the initial thermals that create an initial excited state. There's issue of relaxation and dephasing. All of that go into the model. And of course, then there is the question of, okay, in usually we denote the control as some function C of t. But if you look at the experiment, this is, by the way, the setup at IBM Zurich. This is Jerry Chow. It's not exactly clear where this function goes into this whole machinery. So we have this whole pipeline of how the control function goes in, and then you have the time evolution and the whole process of the readout, which can include a confusion matrix and stuff like that. So we try to build an accurate model of the system. And what we will try to learn in this whole process is the parameters of this model, meaning what is the initial temperature, what is the coupling, what are the qubit frequencies, etc., etc., etc. Right? Because these are devices we build. This is something we have kind of a rough idea what's going on, hopefully, but we're kind of very murky on the specifics. Okay, so we have two optimizations that are model-based. One is the optimal control, the C1, and the last one, which is the characterization, which is the C3. So we do that using TensorFlow. So what we do is we frame and implement the propagation and then the various control functions of the various optimizations as a computational graph in TensorFlow. So it's not neural nets. So some of our nodes are a bit weird. We exponentiate complex matrices and stuff like this. It took a while, but this thing works. And because it's TensorFlow, now we have automatic differentiation. So I can ask things like, what is the gradient of, I don't know, the gate fidelity with respect to the line bandwidth, and get kind of meaningful results. Okay. And I think kind of to our knowledge, this is kind of the most detailed simulator that's out there. And if you like it, you can kind of grab it here. Okay, so now that we have a simulator, we can start kind of playing around with it. So we'll do the model in 3 steps. We have a simple model. Simple model is really trivial. You have 2 qubits, they're isolated. You can see the kind of coupling is ignored. You just think you have 2 isolated qubits and, no noise, no thermals, no dephasing, no nothing. The intermediate model, we bring back the coupling. We're now aware the qubits are coupled, but again, the more complex features are out. And then we have the full model. Okay. And now we kind of start iterating. So we start by doing the optimal control, what we call C1. Basically, please find the control pulses, which look something like this, right? The waveform generator input is piecewise constant, although later you have all kinds of transfer functions that smooth it out and stuff like that, and that's also represented. So the first stage is to find the controls that implement certain gates, and these are the gates we're trying to implement. Now, because we use this really simple model, when we go to the experiment and we do calibration, of course, things change significantly. They start with kind of really bad infidelity and progressively go better. Now, what we do here is CMAS, because this is a kind of a black box situation. So we're using currently CMAS, although we're exploring other algorithms. And we do something known as orbit, which is single length randomized benchmarking. but I think given the time constraints, I won't go into detail what that means. And then the third stage is the characterization or the model learning. And what we have is a match score, and I'll kind of go into that a little bit later. And we're trying to match what the simulation tells us about what it expects the results to be and what the experiment gave us. And by kind of optimizing this function or learning this function, we get to a better characterization of the system. Okay?
Sorry.
And this here, yes.
You got like, yeah, maybe 3 or 4 minutes left. Just a short notice.
Yeah, okay. All right, so I will skip faster. This is the intermediate model. We add a little piece, and this is the full model. And here you can see this, the y-axis here indicates the distance between the model we learned and the actual data. And you can see the initial ones are really bad. They're kind of a few sigma away. And the last one gets to really good values. And another way of looking at how well you reconstruct your experiment is we have a correlation plot of the experiment and the data. And you can see initially there are kind of quite significant deviations, but the last model is good. Now, another point to mention, this is quantum. Everything is always noisy. So you don't expect to get a clear line, right? Because the noise will never match. But at least the width is what you would expect given the noise. Okay, so kind of one more slide about details. So for model learning, the goal function, we use the Mahalanobis distance between what we expect the distribution of experimental results and the model derived distribution. Because again, there's noise in both, so we're comparing distributions here. And this is it's essentially you're kind of counting the number of sigmas, assuming everything is a Gaussian distribution. And it's really binomial, but because we have a large number of shots, we can kind of approximate it as Gaussian. There's a big issue of how do you select the training set out of all the experimental results, because there are a lot. And what we do is we give increased weights to situations where the model does a poor job of recreating the data. We can't do anything Bayesian because we're talking 20 plus parameters and just the dimensionality will kill us. And the optimization landscape we're dealing with is not very convenient. You have a lot of local minima, and we're not exactly sure how to do the exploration-exploitation balance. But this, for example, is a typical landscape, and you don't necessarily start here. You might start here. Now, another nice thing we can do is we can do a sensitivity scan, meaning we change one of the model parameters, and we see how the match or mismatch between the model and the experiment varies. And you can see here that the full model, for example, gets the parameter of the qubit frequency exactly right, but the other models are kind of all over the place and they have very high values. I'll skip a few things. Sometimes we discover that the data we collected is insufficient to localize a parameter in the model, and then we can do another experiment and add it to the pile of data, and that will kind of narrow down the ranges of parameter, and then we can reconstruct it. One slide about future fun stuff, what we're planning for 2021. So we're going to make 2 efforts in the direction of experiment design, meaning we have essentially an optimal control task, either to measure any of the model parameters. You just kind of point to the parameter in the model and ask it to design and execute an experiment to measure that. And the other is, given 2 competing models, to design pulses which will clearly differentiate between them. And then we want to go into generative adversarial learning of quantum systems. And I mean, you probably know this generative adversarial model. So the discriminator will try to find pulses where the model fails to reproduce the experimental results. And the generator is essentially trying to mimic the physical system as best as it can. And then you create this adversarial model where you essentially expand and test the limits of your model and kind of focus the learning on areas where you're doing a poor job. And another kind of generative adversarial direction is to deal with generative adversarial calibration, where the discriminator is trying to get really difficult circuits to the optimal control. Last thing is the error budget, meaning that you can ask a what if. What if I changed my waveform generator bandwidth to, I don't know, 10 times as much? It costs, $100,000 for such a device, but would this improve my fidelities? And there's a V there because that already works and is part of the package. You can get everything at qoptimize.org. If you have any questions, you can send an email to help@. And this is the paper that describes what I've been talking about. And thank you very much.
Yeah, thanks, Shai. Very nice talk. Yeah, so I don't see any questions in the chat or the Q&A currently. Oh, there's one coming up. Okay, let's go with this. So, so if you have sorry?
No, okay, please go ahead.
Yeah, okay. So if you have a high number of qubits, simulating the full model will become classically intractable. And will simulated models working on a small subset of the qubits be enough?
Yeah, okay. So the answer is apparently yes and hopefully yes. Apparently yes, because if kind of you look at all the additional supplementary material to the Google supremacy paper, they note that they don't see any large-scale correlations between their qubits. Meaning, if they measure the performance of, let's say, two neighboring qubits and their nearest neighbor, this is sufficient to extrapolate the performance of the entire machine. So we can do all this work on overlapping plaquettes of, let's say, two qubits, nearest neighbor, maybe next nearest neighbor. I'm saying hopefully yes, because even if you don't believe Google, if we cannot calibrate and characterize quantum devices piece by piece, we're dead. We'll never get it to work. So I'm kind of assuming this whole effort of quantum computation has hope of succeeding. And if it does, then we can do what we plan to do, which is the plaquette approach.
Okay, nice. Yeah, any further questions from the panelists or something? So if it's not the case, there's one.
Yeah, hi Shai. I had a question about when you're doing pulse optimization, how are you able to kind of take gradients and optimize over evolutions or trajectories, for example? So if you have a kind of time evolution and then you integrate over, it's not a simple function or a simple map, it's a trajectory. And then how can you unleash TensorFlow to solve that kind of a problem?
Okay, so if you break down evolution, as an example, superconducting qubits, typical frequency is 5 gigahertz. If you, which translates to about 200 picosecond per cycle, we break down evolution to something like 10 picoseconds. And we assume that the control fields are constant at a resolution of 10 picoseconds. Now, that as a result, evolution is now just a big product of exponentiation of matrices for each 10 picosecond slot, right? So now I can write this in TensorFlow as a computational graph, and then I can do the automatic derivation and everything else.
Okay, so that kind of discretization, and I suppose it works.
Yeah. It works, and you can kind of prove in the practical sense that it's accurate by just increasing the frequency and seeing the frequency of discretization, resolution of discretization, and seeing that the final result doesn't change, to within what you care about, right? So maybe it changes to 10 to the minus 12, but who cares? We care about 10 to the minus 4.
Okay, yeah, thanks.